All right, so the streak just being the color of the powdered form of the mineral. That's the main thing. And the one on the right, well, the one on the left too, is a decent example of something you wouldn't expect. You wouldn't expect the powdered form of that mineral to be kind of that goldish color just by looking at it. All right, the next characteristic test, whatever, is cleavage and fracture. And these have to do with how the mineral breaks. So depending on how the mineral breaks, you can determine if the mineral has cleavage or if it has fracture. And this is something that you don't actually have to break the mineral in order to determine which one it has. You can just tell by looking. So the first one, and I'll actually come back to this picture. The first one, cleavage, is when the mineral breaks, it splits along smooth surfaces. So, in these examples, these haven't been cut, they haven't been polished or anything like that. It's just how the mineral breaks. And because of how the atoms are arranged within the mineral, because of the crystal structure, when it breaks along smooth surfaces. It cleaves. Just like same root words, like a cleaver, like a butcher uses a cleaver to separate. That's what happens to these minerals. When they break, if they have this feature, if they have cleavage, then it gives you smooth surfaces. Just like on this picture, the pieces down at the bottom, if you look at them, they have flat, smooth surfaces, and that's how it breaks. There's that mineral sample, you could say it has cleavage. And there's some different types, sort of, or different, I guess, classes. You could have cleavage in 3 directions at 90 degrees. So, each plane is perpendicular to the other ones. So this is going to give you kind of like a cube type shape as a result, after it breaks. You can have cleavage in 1 direction. So this one actually, another example of this from the notes yesterday, the example for the pearly luster was a mineral that has cleavage in 1 direction, and it's almost like a stack of paper that you can just peel apart. But if you look at the edges, there's nothing flat or smooth about that. It's it's rough, it's irregular. So this just has cleavage in 1 direction. You have it 2 directions. So this one, you can see those 2 faces, and they come together pretty sharp, clean edge. And then you can have 3 directions, but not 90 degrees. So whereas the first one, when they're equal to 90 degrees, it gives you kind of a cube. This is going to be kind of like if you take that cube or a box and then kind of squish it back and then kind of squish it to one side. So it's kind of tilted over a little bit. So, it's not perfectly, it's kind of tilted over and back. But this is a great example of, just the flat, smooth, clean edges that can result from just normal breakage. All right, so if a mineral doesn't have cleavage, then it has fracture. So when it splits with rough surfaces. So you don't really know what it's going to look like. A mineral with cleavage that, like in some of those examples, while every piece might not look exactly like every other piece, you're going to have an idea of what the pieces would look like. Fracture, you don't know at all. It would be like dropping a plate on the floor or a piece of glass. It'll break, but you don't know what the pieces are going to look like. You don't know what shape they're going to be. Whereas a mineral with cleavage, you're probably going to have some idea just by looking at it. You could tell what the pieces would look like. And some different types of fracture. This first one is conchoidal, which means shell-like. And
you go, babe.
That one?
All right, thank you. Thank you.
Nice. So it's shell-like. So up at the top part, you'll see kind of like a shell shape. You see like a little half circle with some striations in it. It kind of looks like a clamshell or something up there. Glass breaks this way. It has this conchoidal fracture. Maybe if you've seen like a glass with a chip off the rim, if you look at it closely, a lot of times it'll have kind of this half circle shape with some striations in it. So that's one type. Another one is fibrous. So it has kind of the splintery texture, after it fractures and breaks. And this is a mineral called gypsum. And some of these fibers, they don't really bend, so you can't really peel them off, but you can kind of break them off into pieces where they're kind of bundled up, but they aren't flexible to where you can just kind of peel them off. It's not like string cheese or something like that. It's they're rigid. And then just irregular is just uneven. It just breaks, but it's it's not smooth, it's not even, it's just kind of, it just breaks, just fractures. And then the next test is the acid test. And somewhere in the notes, I would maybe add in here that the acid test identifies minerals in the carbonate family. So the acid test, if you take hydrochloric acid and you put some of that onto a mineral, if the mineral is a carbonate, it will start to bubble and fizz and it will dissolve the mineral. And other mineral families, it doesn't do anything to, but carbonates, it does react this way with bubbling and fizzing and all that. An example that's kind of close to where we are, limestone, the rock type limestone, which we have here, and we have a lot of it in southern Indiana. It's kind of held together by a mineral called calcite, which is a carbonate. So if you put hydrochloric acid onto limestone, it will start to bubble and fizz and dissolve as it breaks down the calcite that holds it all together. So that's another thing that you can use to determine what a mineral is. Because if you can determine that it's a carbonate, you can get rid of a lot of possibilities if you know that it has to be a carbonate. And then this last little section, I'd mentioned that there aren't very many things that by themselves will tell you what a mineral is. But there are some kind of special, unique properties that some minerals have that are just an instantaneous dead giveaway about what it is. One of those, if it's magnetic, that's a pretty unique property that not a lot of things have naturally. In magnetite, there's a lot of iron that's in the mineral, and sometimes that can be naturally magnetized. The samples that we have aren't magnetically active to the point where they will attract things like this, where paper clips are sticking to it. But if you have a magnet, the mineral will stick to the magnet, which still by itself is not a really common thing at all. Another one is taste. So the mineral halite has a very distinctive taste that any of us would immediately recognize. Does anyone happen to know what halite tastes like? It's in the halide family. We talked about it a couple days ago. Anyone want to take a guess what it might taste like?
Salt.
Good, it tastes like salt. Halite is the mineral name for salt. And the last little part of the slide doesn't really apply because we aren't really here, but it's generally not a good idea just to go randomly tasting things, especially given the current state of the world. Plus, people might point and laugh. But so, now the next time that you need somebody to pass the salt or something like that, you say, "Oh, excuse me, could you please pass the halite?" If they look at you funny, you say, "Oh, sorry, I'm just using the correct scientific name for the mineral halite, which is salt." You can impress your friends and neighbors. And then another unique feature is double refraction. So
you go back real quick, sorry.
That one?
Another one.
That?
All right, and then all right.
Calcite, it has this feature, this quality of double refraction. So if you look at something through the mineral, you'll see double. So just like in these pictures, if it's a good sample that's clear enough, if you put it up against something, as you look through it, you'll see double. And that's just how, it's because of how the mineral bends and reflects light as it passes through the mineral. But it is a unique feature. And then a few other things that the minerals can possibly do. One is a mineral could fluoresce or glow in UV light or like under a black light. And that's actually what this picture is. So these minerals are under a UV light, and so they give off light while they're under the UV light. I'm guessing some of you have seen, fluorescent colors or kind of those neon colors that are really bright, but then if you put them under a black light, they're really bright. Or if you use Tide or laundry detergent or whatever, and you can paint it on stuff and you can't really see it, but then if you put it under a black light, it glows. That's fluorescence. It's giving off light energy because of the UV light. It's affecting it that way. Some minerals can be phosphorescent, so this is kind of the typical like glow in the dark type stuff. You have to kind of charge it up. You put it under light for a while, and then you put it in the dark, and it'll glow. Some minerals can do that. And then some can be radioactive, where they're just giving off energy on their own. This isn't normally in the form of light. It's typically just radiation that's given off. But it is possible to just, that it's radioactive and it's just giving off energy all the time. All right, does anybody have any questions, or are there any slides I need to go back to?
Yeah, I left like for a little part because I have to go to the door. But can you go to the 4th slide?
Give me a second, I'll pop back to them. All right, so here,